Hello, everybody, and welcome to another lecture in Geography 341, Weather and Society. I'm Dr. Zach Hilgendorf, and in this lecture, we're going to be talking about atmospheric pressure and winds. Kind of been building up to this. So we talked about heat and temperature fluctuations. We talked about precipitation, cloud development and formation and types. Now we're going to look at atmospheric pressure and winds. Now, these are really some of the true drivers of change in meteorological patterns across our planet, because with differential pressure, you get increasing winds. So the stronger that difference between pressure in one area to another area, and the closer those are, or the further away they are, that's what drives our wind patterns across the world. So that's what this lecture and the next are going to focus on, is looking at how pressure impacts our meteorological systems. Oops. Now, atmospheric pressure, as you may recall, is just the average force per unit area exerted by randomly moving gas molecules bouncing off of a surface. We typically think this force as being exerted on the surface of our planet, and that's often how we measure it. Typical units we use include pounds per square inch, newtons per square meter, which also equals a Pascal, or 100 newtons per meter squared gives us a hectopascal, or a millibar. Those are more conventional for what we use here in meteorology. So we can think of particles of air as bouncing chaotically around the atmosphere like we see here. Now, you might ask yourself, what determines that? Because we have a pressure that's based off of how these molecules are moving, but there's something that determines that. So what determines air pressure? Well, pressure is calculated through the ideal gas law, which states that pressure, or P, is equal to rho RT. Rho is the density of air in kilograms per meter cubed. T is going to be our temperature in Kelvin. And then R is our specific gas constant. Now that number never changes. It's 287 joules per kilogram per Kelvin. So this gives us our equation of state, our ideal gas law. Now this is how we can determine, based off of the conditions within the atmosphere, what our pressure is in pascals. As temperature and density fluctuate, we see changes in the overall pressure. Now, of course, in the free atmosphere, without constraining boxes in a perfect system, it can be difficult to determine air pressure. However, we can easily rearrange the ideal gas law equation to solve for density rather than for pressure. Given that pressure is determined by the collective weight of molecules over a given space, so constraining it by, for example, a square meter, this equation will yield air density rather than air pressure, and that's a little bit easier to obtain. And we know that pressure is greatest at sea level, right? Do we recall what that is? 101,325 newtons per meter squared. That pressure can be converted to things like hectopascals or millibars as well. And it really is just the assumed weight of the atmosphere in a 1 by 1 meter square on the surface of our planet. We can convert that to 101,325 pascals, 1,013.25 hectopascals, or 1,013.25 millibars. They all mean the same thing. They're just different versions of the same number. Now, if we increase our altitude from 0 to 5 kilometers, we basically decrease our pressure to about half the atmospheric pressure and density at sea level. This averages out to be about 540 millibars at 5 kilometers of altitude. Rising up to about 10 kilometers, we drop to about a quarter of the atmospheric density and pressure, right around 264 millibars. We jump up to 15 kilometers, we drop to 12% of the atmospheric pressure and density, and drop to about 120 millibars. And there are pretty consistent relationships between atmospheric pressure and altitude. Here we can see a graph of standard atmospheric pressure and altitude. You'll want to use this graph in the next couple of slides, so pause the video and take a screenshot of this, or use the PDF file of the slides for reference. But this trend closely mirrors that of atmospheric density versus altitude, which we can see here. So what is the atmospheric density of air at sea level? Well, Using that reorganized ideal gas law where density is equal to pressure divided by the specific gas constant times temperature, we can figure this out. We know that the pressure is 101,325 pascals at sea level. You can see our equation down here. But we can also use the relationship between pressure and altitude from the previous slide. Now, temperature is a bit more difficult to determine sometimes. That said, NASA provides some calculations to determine our temperature with altitude. It's that equation that we see down here in the bottom left-hand corner. In the troposphere, and this is only in the troposphere, we can assume that temperature in degrees Celsius is equal to about 15 minus 0.00649 times H, where H is our altitude. To convert this to Kelvin, we just need to add 273.15 to this value, which is what we see here. Knowing these equations and values, try to figure out the density of air at sea level with, even though you may already remember it from a few slides back. So go ahead and pause that video for just a second. We can see our equation here. Did we get 1,000 or 1.225 gram or kilograms per meter cubed? That's standard atmospheric density. And that's something we hold constant. A lot of modeling equations will use just that number, 1.225 kilograms per meter cubed. All right, now let's give this one a shot. The density of air at 5 kilometers or 5,000 meters is equal to what? Go ahead and pause the video and see if you can figure it out. All right, here's our equation. 54,000 pascals divided by 287 joules per kilogram per Kelvin times 255.65 Kelvin gives us about 0.736 kilograms per meter cubed. So why is pressure such an important aspect of our climate? Well, differences in pressure, which are driven by things like topography and temperature, drive the flow of wind across our planet. And that's where we're going to go next. We're going to talk about atmospheric wind patterns and how wind moves across the planet. First off, we're going to go ahead and talk about a fundamental scientific law. That says that air always flows from high to low pressure, pushed by a pressure gradient force, unless something keeps it from doing so. Pressure gradient is just the change in pressure per unit distance. We can think of it as the difference in pressure between 2 points divided by the distance between those 2 points. So, for example, we can think of a soda can. The second you open it, you'll hear that telltale whooshing noise as the pressurized can rapidly equilibrates to the atmospheric pressure around it because that can is pressurized. So we can think of that as kind of an intangible pressure gradient force. The vertical pressure gradient at sea level is about 0.12 millibars per meter. This means that the vertical pressure gradient force on a cubic meter of air is about 12 newtons. Right about here. This balance between the weight of air and the force applied on it is what we call hydrostatic equilibrium, which basically just refers to the balance maintained between the force of gravity and the vertical pressure gradient that does not allow air to escape to space, which is really kind of crucial for us to live where we do. So what is wind then? Well, wind is just air that's moving horizontally in the atmosphere. It's caused by a pressure gradient force pushing air from areas of high pressure to areas of low pressure to equalize the difference in pressure. So wind is really just an expression of the horizontal difference in atmospheric pressure. We can see two maps here. One from the 2nd of March and the other from the 5th of March with isobars denoting lines of equal pressure. Isobars are typically expressed in reference to sea level pressure in millibars. We see a high pressure system. We see a high pressure system moving west across the continent, while a low pressure system is moving southwest. So if we look here, we see here's our high pressure system in time 1, and we can see that it's somewhere, Kansas, Nebraska area, right around here. And it has moved about due west or so. And we can see here, this low pressure system is being pushed. It's about right over here, Hudson Bay area. It's being pushed to the southwest here. So we can pick out and name certain features for those pressure maps. For example, we call this type of low pressure system here and here, kind of this concentric ring formation that we see here. This is a cyclone. So it's basically just an area of low atmospheric pressure characterized by rotating and converging winds and ascending air. So they're converging at the surface, and we'll see some diagrams of this here later on. And ascending, we talked about some of these when we were talking about our forces that cause air parcels, that cause air parcels to rise. We talked about that, and we'll see it here very soon again. Then we've got these type of kind of divergent high pressure systems here. We call those anticyclones. If we have a kind of elongate shape of a low pressure system, we call those troughs. If we have the same thing, but for high pressure systems, we call those ridges. We see another one there. Now, it makes sense that there are all of these differences. We have some major topographic features and barriers to the flow of wind across just our continent alone. We've got this kind of no topography, flat zone over the ocean on both sides of us, here and here in the Pacific and the Atlantic. We've got this major barrier to flow here, the Rocky Mountains, for example. Same thing throughout California, the Cascades, the Coastal Range, the Sierra Nevadas. All of these things can impact the distribution and pressure differentials between air parcels moving across our planet. So let's go ahead and look at the difference in horizontal pressure gradient force between these 2 points here. So going from 1036 millibars to 1032 millibars. So that's a distance of about 300 kilometers. So we typically look at this in meters, or we can use kilometers as well. 300,000 meters, 300 kilometers. But all you have to do is take the difference between the pressure at those two spots, 10,036 minus 10,032, that's just 4. And then you divide it out by the horizontal distance, so 300 kilometers or 300,000 meters. And if we were doing this in meters, you'd get 0.000013 millibars per meter. That is our pressure gradient force. A cubic basically what we're saying here is the horizontal pressure gradient force on a cubic meter of air is 0.0013 newtons. How about up here? So here we're going from about 1024 to 1016, right? So notice the isobar lines are a lot closer. Now, if we remember anything about contours and how these types of lines, isobars or isolines or contour lines in general function, notice how much how closer together all of these are grouped versus how broadly spaced the isobar lines were from that first example. So here, the distance is only 200 kilometers, and we went from, again, 1024 to 1016. So there we've got a pressure gradient force of 0.00004 millibars per meter and a horizontal pressure gradient force on a cubic meter of air of 0.004 newtons. So a much stronger pressure gradient force between those two positions than between the first example. Now, you could expect then that the winds would be substantially stronger going from Hudson to maybe Wausau area, the Wisconsin version up there, versus going from kind of central Texas to maybe Houston or the coastal area of Texas there. So next we could ask ourselves what causes horizontal differences in pressure. So we talked about what is wind and what causes wind. But what causes these different pressure or these pressure differentials? Well, the primary causes are differential heating of the atmosphere, which we talked about in one of our previous videos. These include things like thermal lows and thermal highs, as well as changes in the speed and or direction of winds aloft, which include things like dynamic lows and dynamic highs caused by the convergence or divergence of winds in the atmosphere. So let's look at these causes a little bit more in detail here. Let's start by thinking back to the difference between cold and warm air masses. We talked about these just a couple weeks ago. Recall that warmer air masses contain more excited molecules of air, causing the air mass to expand, leading to lower density within the air mass and a rising mass in general. Air molecules in cold air masses are not as excited and are denser. So if we were to look here, this example, if the mass was warmer than the surrounding air, it would rise because the mass would be of lower density. So this means that there would be diverging air aloft and converging air at the surface. Remember that because we have a warmer parcel of air, those particles are more excited, that density is lower. So near the surface, you have a lower pressure system. So air is going to be rushing in to fill that low pressure system. Now, at altitude, say 500 millibar level or 5.6 kilometers roughly or so in the atmosphere, what you're going to have is a high pressure system. So what you get is kind of these converging winds at the surface, diverging winds aloft because they're rushing to fill out the low pressure spaces around them. So you can kind of see how that sets up here. Now, we call this surface convergence, divergence aloft. What does that look like? This, in kind of three-dimensional format. So at the low pressure system there, we've got convergence coming in. Get my little pen tool here. Kind of rushing into the surface here. Kind of at this off angle. We'll talk about why that is here in just a little bit. Here's our lowest pressure cell here. That warmer air is going to rise and cool adiabatically as it does. And we have this higher pressure system here where it's higher pressure than the rest of the atmosphere around it. Notice here we kind of displace, back in the middle of our diagram here, we displace that 500 millibar level. So that wind is going to be rushing to fill the lower density spaces around it. So what about a thermal high pressure system? So here we can see our setup. We've got cooler air at the surface. What do you think is going to happen to that 500 millibar level? Well, it's cooler air, so it's denser air. So you're basically going to displace that 500 millibar level down in altitude. So what do you think is going to happen here? Well, we're going to have a low pressure system aloft, so there would be converging air aloft and diverging air at the surface. So at altitude, a low pressure system, at the surface, a high pressure system. Here we have subsiding air, so air dropping instead of air rising. In this situation, we would have a kind of air warming as it descends adiabatically again. And you can see what that looks like here. You've got converging air at the surface, and it's rushing out converging air at altitude, I apologize, and diverging air at the surface. So it's rushing away from that high pressure system as air is descending into it, kind of piling up again, leading to a higher pressure system at ground level. So the pressure gradient force is one of the main factors affecting wind. It causes wind to blow, and the steeper the pressure gradient, the stronger the pressure gradient force, and the faster the winds. The next major force affecting wind is the force of friction working against the wind. Earth's surface exhibits a drag force in the opposite direction to that the wind is blowing. The strength of that drag increases as roughness increases, it increases as wind speed increases, and it decreases with distance from the surface. No frictional force exists above what we call the planetary boundary layer. And we talked about that, I think, earlier on here in this semester, which is the portion of our atmosphere that's affected by the drag force from the surface. This is typically or roughly 1 to 2 kilometers thick. We can see this expressed by a figure in a seminal work by Stephen Wolfe and William Nickling in 1993. We can see that wind increases rapidly until it reaches that free stream velocity that we see here, kind of highlighted by my pen there. However, when the surface is much rougher, in the case that we see off on the right here, that boundary layer is displaced, and the bottom of the boundary layer is displaced vertically to roughly the top of the roughness feature. So it takes that much longer for that atmospheric boundary layer to kind of kickstart and us to reach free stream velocity at altitude. This is really important. Think of major barriers to flow like mountains or major metropolitan areas with very large kind of core city districts. Things like skyscrapers and massive businesses and stuff like that. Finally, we're going to talk about the Coriolis force. So this is the force exerted on wind due to the rotation of our planet acting at a right angle to the direction of wind. Wind does not cross isobars at right angles, given this force from rotation. The Coriolis force does not itself generate wind. It modifies the direction of airflow. In the northern hemisphere, winds are deflected to the right of their path of motion. In the south, they're deflected left of their path of motion. So let's pretend that we can throw a ball with incredible force from the North Pole, where we're at. We can see kind of our spinning position on the image on the right, towards our friend who is positioned somewhere along the equator. If you throw that ball straight towards your friend, thanks to the rotation of the planet from this position, by the time it gets to the position of your friend, the position you threw it towards, the Earth will have rotated. And the force of that spinning globe will have deflected the ball towards the right. So we would have completely missed our friend. Likewise, if we were to attempt the same thing at the South Pole, where we can see our rotation is the opposite from our reference frame from the North Pole, we have our ball here. Instead of going to our friend, we can see that it is deflected towards the left. Now, it's also important to note that the strength of that Coriolis effect increases as wind speed increases and increases as latitude increases as we get more poleward. So let's go ahead and look at a graphic to kind of highlight that last point there. So here we can see that graphic, and notice as we get closer and closer to the North Pole in this example, we see larger and larger deflections based off of that Coriolis effect. So we can see our key here during weak winds, how far we're displaced, and during strong winds, how far we're displaced. But it weakens as you get closer and closer to the equator. So let's take a closer look at how these three forces impact winds cumulatively. So if we were to look at a molecule of air being moved by surface winds, the pressure gradient force is always going to be acting perpendicular to those isobars. The Coriolis effect is acting at a right angle to the motion of direction of the wind and pushing it towards the right, and the force of friction is pushing it opposite the direction of motion. As the pressure gradient force is stronger than the Coriolis effect and the friction force, the molecule is pushed from higher to lower pressure. However, we can see it's pushed off course from directly perpendicular to those lines. The direction of the Coriolis and friction forces remain consistent relative to the direction of motion. There's still a pressure pushing against the molecule as it's moving towards the zone of lower pressure. In the case of the higher latitudes, this deflection is due to the Coriolis effect, and it is much stronger than in the lower latitudes as we just looked at. Now, as a whole, in that scenario we just looked at, winds would be moving in this direction, kind of, we could maybe say northeast if we're assuming north is up, as we see our little arrow on the left side there. If the strength of the pressure gradient force was significantly stronger than that of the Coriolis and friction forces, or if we were in the lower latitudes, we would see significantly lower deflection relative to that in the higher latitudes. Overall, winds would look more like this. Notice how much more vertically or northward they're facing rather than before, where, we'll just draw one, they were much more like this. We see a little arrow right there. In the case of low pressure systems, that pressure gradient force is always towards the center of the system, the zone of lowest pressure, while the Coriolis effect leads to the rotation of the system, and the friction force opposes that movement. We generally see these as counterclockwise rotating systems. This is a perfect example of one of those counterclockwise rotating systems. A mid-latitude cyclone is what we were looking at here. So we see our low pressure system kind of right over Wisconsin in this example here. And we can see that winds are coming in at a variety of different angles coming around this system, all pointing and flowing inward, giving it that very, very typical counterclockwise rotational system. Now, this is a cyclone, is what we would call it. There is another one. The high pressure system is an anticyclone. We'll talk about that here in just a second. But first, here is another perfect example. So we're looking at a moisture map of coming into the coast of California. So this is a cyclone or a low pressure system that is in full cyclogenesis, so it's rotating around and around and around in that counterclockwise motion. And we can see kind of that moisture leading into the center as well. So these, again, are examples of low pressure systems. Now this is different than a high pressure system. In high pressure systems, we see those winds generally deflected outward by the pressure gradient force in a clockwise direction rather than a counterclockwise direction. However, if winds are aloft, so at altitude, at some altitude, we can assume that frictional forces are not affecting the flow of winds. So it comes down to the pressure gradient force and the Coriolis force as being the dominant things that impact wind across the kind of middle atmospheric portions. So anywhere from maybe 500 to 200 millibars. Here, where air density is less and pressure is lower, the impact of the Coriolis force deflects winds much more substantially. So we can see here our pressure gradient force and our Coriolis force leads to a significant deflection of winds. And we can basically come into balance with the pressure gradient force, turning winds parallel to the isobars. Let's see here. Rather than kind of being deflected. So those winds can look more like this. So when we look at winds higher in the atmosphere where isobars are relatively straight and evenly spaced, we often see winds flowing in roughly straight lines parallel to isobars rather than perpendicular to them, kind of perpendicular to along with that pressure gradient force. These are what we call geostrophic winds, which are generated when a balance is reached between the Coriolis effect and the pressure gradient force. If these winds are flowing predominantly east to west, we call them zonal winds. Recall back to our definition of troughs and ridges as well. Trough is just a elongate low pressure system, where a ridge is an elongate high pressure system. Where these isobars for circular cells of either high or low pressure, the isobars follow highly curved paths, and the wind flows roughly parallel to the curved isobars, kind of like this. So these are called gradient winds. See here in our high pressure system. So these are called gradient winds, which result from the balance between the pressure gradient force, Coriolis force, and centrifugal forces in winds aloft. So these can lead to what we call meridional winds, which follow a predominantly north to south flow pattern. So that's all we had for this one. We talked about atmospheric pressure, what are winds, and what causes horizontal differences in pressure. In the next one, we're going to look at some global patterns that kind of set up typical weather patterns we see throughout the year in our continent and elsewhere. So hope you enjoyed the video, and we will see you in the next one. Thanks.